One of the things that we're going to be doing in the next few sections involves some summation and summation notation. So I just wanted to take a little bit of a time to talk about that notation and make sure that we feel like we can understand what it's doing. So summation notation has a tendency to, it works with summations that are in a particular format. So here is one type of example. If I am looking for the sum of the first 12 square numbers, for example. So each of the terms of the sum has a has the same format. So each term is a square. So the one way to write this is just to write this is 1 squared plus 2 squared plus 3 squared plus 4 squared on up to 12 squared. Now, if I wanted to talk about the first 12 square numbers, that's pretty easy to write down. But what if I wanted to talk about the first 200 square numbers? Now, if I wanted to write that in the same format that I wrote the previous one, then I would probably not write all 200 terms. I would put a ... in there. I would set up what the pattern looked like and then put a ... But again, what we see here is we see that every term looks the same. It's like 1 squared plus 2 squared plus 3 squared. And so we want to find some sort of shorthand notation for saying I square numbers starting with 1 and ending up with 200. And so that's what this summation notation does. That summation notation reads as the sum of terms that look like I squared, where I starts at 1 and ends at 200. Okay, so that is a shorthand for the above notation. And by the way, that symbol is the Greek capital letter sigma. It's the capital sigma. There's capital sigma and lowercase sigma. It looks like that. So that's basically the Greek version of the letter S, and so S for sum. All right, so a couple of examples. Let's look at this example. So I read this as the sum of terms that look like 2k plus 1 over k squared, where k starts at 3 and ends at 50. So if I am to write out the terms, this would be, I start at 3 and I put in 2 times 3 plus 1 over 3 squared, plus the next number is 2 times 4 plus 1 over 4 squared, plus the next number would be 2 times 5 plus 1 over 5 squared. And I would keep going until I got to 2 times 50 plus 1 divided by 50 squared. All right. This is not the point of this, but I can tell you that you can put this into Desmos, and that is approximately 9.37, those 50 terms. And if you put this into Desmos, basically if you write the word SUM in an equation line, then that automatically pops up a sigma with an n equals blank and blank. And so you basically fill in those blanks and then you fill in the blank after it, of course. All right, let's look at another example. So this is the sum of terms that look like 5 times n, where n runs from 1 to 100. So this is going to be 5 times 1 plus 5 times 2 plus 5 times 3 plus all the way up to until I get to 5 times 100. Next, let's look at this example. So you may not think of this as a sum, but it is, in fact. And this is a little bit of a teaser to Calc 2. So this is, 0.3333 repeating, right? And if I think about what this number means, each of these place values it represents 3 of a particular place value. So this is the same as 3/10 plus 3/100 plus 3/1000 plus ... infinitely, which is going to be a sum of terms where the terms look like 3 divided by 10 to the nth power, where n runs from 1 to infinity. So here, this is actually an infinite sum. Now, in this section of the book, we're going to be looking at a lot of these types of sums, the Riemann sums, where it is each term is f of some x value times the delta x. And so if I was to write this in summation notation, this is going to be the sum of things that look like f of x sub I times delta x. I is the thing that's changing in every term, and I here starts from 1 and ends at n. Okay? And this looks slightly different than this other sum, where here we have a sum of terms that look like, again, f of x sub I times delta x, where in this case, I runs from 0 to n minus 1. Last note on this is just that we have the index of the summation is something that can change. So like, it's just like, I can name something, I can name a function using x as the input variable, or using p as the input variable, or using any letter as the input variable. So for example, when I take this sum of 5n, terms that look like 5n, I can rewrite this also as the sum of terms that look like 5k, where k is the index variable, k goes from 1 to 100. I can write it as the sum of terms that look like 5 times I, where I goes from 1 to 100. It doesn't matter. Those are all the same thing. It's just that one variable tells you what is the thing that's changing with every term. And the most common ones are for you to be used in summation notation are essentially n, k, and I, but don't get thrown off if you see other letters used as well. I think for the most part in these next couple sections, we're mostly going to be using I.